You may start whenever you're ready.
So good morning, everyone. Hello to the people in the online public. I think there are someone connected. So let me introduce myself. I'm Jonatan Romero. I'm a PhD student from the University of Huelva in the Department of Earth Sciences. And these are some of my colleagues who have contributed in some way to this work. And also, I have to thank the organization for letting me present my work and inviting me to the summer school, obviously. Here's the QR code of my research group, which is called Mineralogy and Environmental Mineralogy and Geochemistry. This is the QR code for the webpage if you want to check it out. So I will be introducing you a direct application of modelization to the acid mine drainage problem that we have in the province of Huelva through our work, which is called hydrochemical model of an acid mine drainage affected watershed, which is the Odiel River Basin. I will introduce you the current environmental state and possible remediation action through modelization. So first off, with introduction, I will give you some background on acid mine drainage. However, Delisa has already told you a bit about it. So basically, when a water body of clean water stream, for example, comes in contact with metal sulfides in atmospheric conditions. By atmospheric conditions, I mean aerobic conditions, right? I mean oxygen is dissolved in the water. It destabilizes the metal sulfides by oxidizing it. Mainly, it occurs the oxidation of iron sulfide, which is a pyrite, basically because of its abundance in nature, and obviously it's abundant in the Iberian Pyrite Belt, which is our geological context of the study. Sorry. So this interaction and this oxidation release an extreme acidity, extreme concentrations of sulfates and metalloids to the water bodies, severely and deeply polluting the water bodies through a process known as acid mine drainage when anthropic mining activities are involved, right? So because of its naming English is basically AMD, right? And I have put here something that is very important is the bacterial activity. Why? So the reaction, this oxidation of metal sulfides, is actually a very slow reaction. So the thing is that the bacterial activity catalyzes this reaction, exponentially increasing the oxidation. And that's why we have the big problem of the acid mine drainage, because of the bacterial activity, actually. So to put you in some context of how, for example, in the Iberian Pyrite Belt, because of these 100 abandoned mines, well, not all of them are abandoned now, but most of them are producing now acid mine drainage leachates to the water bodies of the Odiel and the Tinto River watershed, deeply polluting its waters, the waters, and contaminating it all. So to put in some context of the problem, from the total global flux of zinc and copper by rivers to the ocean, through the storage system in which it confluences the Tinto and the Odiel rivers. So around 37% of zinc and 15% of copper is coming from those two rivers to the ocean, to the Atlantic Ocean, from the whole total flux of the rivers to ocean. Was the portion coming from these two rivers. We have also the problem that acid mine drainage can last for like thousands of years. So maybe we have to take in consideration that thing. So here I put you some examples of the acidic leachates coming out of mining tailings. For example, I think this one is the same as Delisa. This is the Thesis one. So maybe it has like something like 30 grams per liter of sulfate. We have measured even negative values of pH there, which is something kind of strange. You can see those very big different colors because of the different concentration of metals. And so these all of these lithiates are reaches the water bodies, water streams, such as the Odiel or the Tinto rivers, deeply polluted. This is, for example, the confluence between the Odiel River and the Agrio Creek. The Agrio Creek is the river which receives all the lithiates from the Rio Tinto mine, Rio Tinto mine, which is very famous. And it's like an irreversible place for the contamination of the watershed, actually. So here also are some peat lakes where there's an immense accumulation of or a high volume of AMD. So basically, with the environmental situation of the Odiel River basin, we can explain that from two main perspectives. The pollution levels. So, of a total of around 100 kilometers of rivers, something like 450 kilometers are deeply polluted by acid mine drainage. We have established three main sources of contamination, which are the Rio Tinto mine in the Odiel subbasin, the Centeno mine in the Oraque subbasin, and the Thesis mines, both in the Oraque subbasin and the Meca subbasin. So here I can show you. These are more or less the concentrations before the confluence with the Agrio Creek, which comes from all those acidic lithiates from Rio Tinto. And as you can see, concentration exponentially increases after the confluence. Also, the pH decreases. It is estimated that of the total acid load of the Odiel River, the Agrio Creek accounts for 40 to 60% of the total acid load. That is why it's the point of no turning back for the Odiel River. So in the case of, for example, the Oraque subbasin, we got it almost polluted from its birth. Here is the San Telmo lithiates, which obviously increases the concentration, decreases the pH, increases the conductivity. By the entrance of some clean waters, concentrations more or less gets diluted until they confluence with Aguas Agrias Creek, which comes from Thesis mines, and then again concentrations and pollutant level increases almost in the lowest part of the Oraque subbasin. From another perspective, we have the Meca subbasin, which is totally contaminated by the Thesis lithiates, and here we have a reservoir which is called Sancho Reservoir, totally polluted. It's an acidic reservoir. It's useless mostly. So basically, these two diagrams or graphs shows us the levels of pollution along the watershed. Here are the lithiates in a Ficklin diagram. Ficklin diagram is pH versus the addition of some major elements. So here we have you cannot see it, but from 2 to 3 main pH values, and this is a logarithmic scale, and it's up to and above 100 milligrams per liter of metals and metalloids, and those acidic lithiates, which is the main Tinto and Odiel rivers. In the Tinto Odiel river, we have something like 2 to 5 pH values, and between around 10 and 100 milligram per liter of concentration of metalloids and metals. However, this is from 2007, and nowadays the pollution values are even worse. So we have on the other hand, we have the administrative and socioeconomic constraints. We have the European Water Framework Directive, which aims for achieving a good ecological and chemical quality of all of European conditions, with the exceptions of more extreme conditions like this in the Odier and the other watershed. But it is also applied to this to the other watershed, and we have water needs. We undergo a strong drought in the Iberian Peninsula. We lack water resources, and in the case of the Huelva province, we are strongly, our economy is strongly based on the red berries industry, and the red berries industry consumes like a lot of water, but there is no water, right? So basically, there is a planification for the construction of a reservoir in the lower part of both Odier River and Oracle River. However, you may guess there are several serious doubts about the water quality reaching the reservoir. And for example, this is an image that is very descriptive of our problem. So here you have the tank works at a standstill, because we need to study the hydrochemical conditions of this place. You have here the Odier River with that characteristic red color because of the acidity. And in the background, you have the Sancho Reservoir, which is mostly acidic with a pH of 4, and receiving all the contaminant load from the Meca Creek, which accounts for 420 tons. Sorry for the Spanish here. 420 tons per year of aluminum and 150 tons per year of zinc. So you can imagine what will happen in the reservoir which is called Alcohol Reservoir, because the Oracle River and the Odier River, the pollutant load is even bigger than the Meca Creek. So we need remediation measures to tackle the contamination of the watershed, right? So, for example, Delisa has talked to us about the treatment plant, for example, the passive treatment plants. We can also put pressure on active mines in the Iberian Paddy Belt to put active treatment plants, for example, or other kinds of remediation like the sealing of adits, or maybe the management of abandoned tailings, hydrological correction to reduce the contact of water with the sulfides. But that costs a lot of money. So we basically have to delimit strategic points, right? Where are we putting our money into, right? So an approach for this is making a model of the whole watershed, of the different confluences. So we call this a mixing model. We have used the geochemical model FIXI. Okay. And this is an example of the mixing model sequence of this part of the subbasin. So we basically have the main stream, which is the Odier River, and other confluences and different entrances of acidic leachates. For example, the ones from Concepcion mine. We use the common blocks mix equilibrium phases. If you remember equilibrium phases from the previous day, we use that for equilibrate the water with some mineral phases or the atmosphere or whatever. Right. So basically, we mix both the Odier River with the Concepcion mine. We use the common block safe solution, and we use that solution for the next conference. For example, in the conference of the sample with the acid mine drainage from Sampleton mine, right? So this is basically the series of commands used in Thesis for modeling mixing processes in the different confluences. So for the mix command block, we need a mixing reactive, which is basically how much one of the members of a mix puts into the final mix, right? I don't know. For example, if we have like in ideal conditions of flow rate, if we have the audience with 10% of 10% of milk. I mean 10 milligram per liter of sulfate, and concession mine has 90 milligram per liters of sulfate. More or less, their mixing ratings will be 10% for Odile River and 90% for concession mine. But this, in the case of ideal flow rate, which accounts for example, if the flow rate of the Odile River and concession mine is the same, which is actually not the same. But basically, we calculate mixing ratios through theoretical calculation based on conservative element concentrations and flow rates of the mixing members of the different confluences within the watershed. Why we use conservative elements? Because we have to make sure that in the different confluences, that element is not precipitating in any mineral phase. It remains dissolved in the water, right? So once we have the whole mixing model, we can estimate what will happen if we, for example, simulate a remediation action. I don't know, in convection mine, for example, we can modelize a treatment plant with that's passive treatment technology, which is the dispersed alkaline substrate, which Elisa talked about before. With that, we have an intense reduction of contaminants in the model treatment output water. pH increases about 7, and there's a complete removal of dissolved acid-generated metals such as iron and aluminum. Right. So we save that. We save that water, that simulation of a treatment plant, and what will happen if we reduce these the pollutant loads of this acidic leachate? What will happen in the next confluent with another acidic leachate? Obviously, because that leachate is treated, the next one will be somehow neutralized, right? Do you understand what I? Okay. So more or less, these flux. These are two flux diagrams. This accounts for the Orake subbasin, and this accounts for the Odile River subbasin, right? So those are the different confluences within the subbasin. And to simplify, I'll put you an example of what we can do with this. We have modeled two scenarios, mainly the reduction of the main AMD producing sources, which are, again, Rio Tinto mines, San Telmo mine, and Tarsis mine, right? So what will happen if we reduce 50% of the pollutant load of those mines? Or what will happen if we reduce 100% of those sources, right? So basically with this, the model should represent the hydrochemical conditions and the AMD contamination along the other watershed. It should allow us to estimate the evolution of the water quality of the Odile drainage network after the application of restoration measures. And with this, we can have like a hydrochemical model as a management tool for the Odile River basin. Obviously, we have to validate our model. how do we do that? So because we are modeling mixing processes, we need the actual chemical composition of the different confluences, right? So basically, we compare the estimated values via the modelization versus the measured values in the fieldwork and also in the laboratory analysis. So as you can see, conservative elements in this ranges of pH, conservative elements such as aluminum and sulfate, more or less are the same. So we can guess that the mixing processes via the flow rates are more or less accurate. pH is more or less accurate as well. However, there are some pure adjustments at the upper part of the Arche subbasin with iron. This is probably because, this is because of ideal condition of modelization. For example, in terms of equilibrium, we force Frixie to equilibrate with, for example, Shermanite, which I haven't talked about. So we, in the equilibrium phases, we equilibrate the water with Shermanite, basaluminite, gypsum mostly, because those are the mineral phases controlling the hydrochemical condition of the rivers. So because we force that equilibrium, this overestimation is probably because of some kinetics that are not involved in the model. Here I show you the map of the other watershed and how it is affected or less by acid mine drainage. So we will focus on the results of the water quality after the remediation, the simulation of the remediation measure in what we call OD9, which is the location for the future Alcolea reservoir. So we see here the results of the different reduction in the model and the original conditions. So to be honest, the 50% reduction is more conservative and more realistic than the 100% reduction, which in most cases is almost impossible, to be honest. So we see a significant reduction of major dissolved elements in the water quality reaching the Alcolea reservoir. For example, we see more than 50% of major elements have reduced in the simulation of the 50% reduction of the three main AMD sources. And for the optimistic and realistic 100% reduction, we see that almost everything has almost everything has gone out of the water, with some remaining sulfate because of a more conservative behavior. But for example, we may have a water quality with conditions that are recommended by the Farming Agricultural Organization, and we may use then that water reaching the reservoir for agricultural purposes, right? However, the pH would not reach neutrality in any of the model scenarios. Why is that? Probably because of the relevance of minor A and B discharges on the pH of major receiving water courses. For example, because the nature of the scale of pH, which is logarithmic, a minor discharge with a pH of 2, for example, reaching a main course with a pH of 7, it will probably reduce the pH of the main water course for about 3 points of pH, I think, maybe. So, going into conclusions, we see here how the water quality along the whole watershed after the modernization of the different reductions, we see that the lower part of the different subbasins have transformed from moderately affected by acid and mine drainage to clean waters or slightly affected, with the reduction in concentration of the Rio Tinto mines, San Telmo and Parsis mines. So we obviously, like every model, we have some limitations, and this is a simplified model, which needs to be improved, obviously. So one thing which is important, very important, is that it does not represent a hydrological year. Why is that important? Because the hydrochemical conditions of the watershed is strongly dependent on seasonal variations. So, for example, in the wet period, more or less, the dominant process is dilution because of the irrigation by precipitation or whatever. However, during the summer, evaporation occurs, right? The precipitation of evaporitic salts occur, and they work as a temporal and unstable storage of pollutants. And with the beginning of the wet season and the first rain, all of that precipitated gets dissolved, putting into solution extreme levels of acidity, right? Which accounts for the major peaks of contamination of the year. So we need a model for every season, more or less, right, to represent that hydrological year. Again, the limitation of the reaction kinetics. So we mostly force mineral equilibrium in modelization. So basically, all iron, for example, if we equilibrate with shermanite in a mixed process, in a confluence, all iron will precipitate until reaching equilibrium, which should not occur in reality because of kinetics and reactive transport. Also, there are some diffuse clean water inflow that we cannot account really. However, we can put this as a management tool for the Oder River Basin, defining strategic points of action and establishing an order of priority of those remediation action I was talking about before. We could establish new perspective for improving the model, like apply the model to different remediation scenarios in the basin. For example, what will happen if we only reduce the pollutant load of the Rio Tinto mine, or create other models for different hydrological conditions or situations. And also evaluate, we have to, for the future, evaluate the pollutant load that would reach the alcohol reservoir during a hydrological year to see how the water quality will evolve in the reservoir. So that is all. Thanks so much for your attention, for letting me present my work. I would appreciate questions or suggestions to feedback to improve this. Thank you so much.
Well, thank you, Jonatan, for your presentation.
Was it good on time?
Yeah, perfect.
Okay.
If you don't hear me, it means you're on time. Thank you so much. Do we have some questions in the crowd, maybe? Yeah, you can go ahead.
So for what I understand, you impose a reduction of pollution, but you don't consider any treatment. It's just
it's over optimistic, to be honest. But you can do demonstration of a treatment plant, for example, at different points.
So that's my second question. My question is, because now you consider like 50 and 100%. What is the kind of rate of treatment if you put a passive treatment plant?
It depends on the acidity of the leachate. For example, the Concepcion and Esperanza mines has already treatment plants working on there.
Yeah.
Well, Concepcion more than Esperanza, but whatever. And the pH of the output water into the main Odile River reaches neutrality, and it has alkalinity. So you can guess that most of all of the acidity has been consumed or neutralized in the treatment plant. So you may guess that there is a 150%. Yes, the 50% is a more conservative way to.
Okay.
Because, for example, 50% is more like if you do a management of tailings, like some hydrological correction. For example, I don't know if I can. Wait a second. Can I close this and open Google Earth?
Yeah, of course. You're not, your screen is not on stream anymore.
So I will show you the location of San Telmo mine and put you an example of our hydrological correction we can do there. In the meantime, any other questions?
Yes.
I have a question. Yeah, you consider like this kind of sequential treatment, or let's say, so why would it not be possible just at the confluence of all the rivers to do something there? Because you will always again get ingress from the other mines, right? So just to do it at the ends instead of putting different places.
So we do that in different places in the sources of AMD, because, for example, for treatment plant are very dependent on flow rate. So most confluences, the flow rate is very high to put their treatment plant. So you have to put the treatment plant on the source, which has a lower, obviously, flow rate. That is a matter of the functioning.
You could not put it just before the Alcolea reservoir, something.
No, it's impossible. It's impossible.
Okay.
Yeah, actually, I tell you that from January to May, dilution processes are the main dominant process in the watershed. However, because the flow rate is so high, actually, you have diluted concentrations, but the pollutant load is very high because of the flow rate.
Yeah, okay.
Even if you have those minor concentrations. So it's the treatment plant is dependent on the flow rate. That is because we cannot do remediation over the confluences.
Yeah, and for the modeling, you only consider major elements for the moment, right?
Yeah,
heavy metals. Or...
Yeah, we can couple that because so basically iron and aluminum mostly control the hydrochemical condition of the AMD because of those precipitation and absorption processes occurring within the, for example, Shermanite has a lot of preference for arsenic cadmium layer.
So you assume they are co-precipitated with these major phases.
Yeah, but in this case, because we do a reduction of the pollutant load, I can actually show you the other elements as well. But we do not consider co-precipitation and absorption.